Hey, my name is Elizabeth Lobo, and I'll be discussing the findings of my current work. Let's not make a fuss about it. In the field of privacy-preserving statistical analysis, there is a very robust technique called differential privacy that adds calibrated noise to the query's results before the publication. The calibration of the noise is very important to preserve the privacy without compromising so much on accuracy. In a nutshell, this noise depends on a privacy parameter epsilon, which the analyst provides, and the global sensitivity of the query, which quantifies how much its output can change if there is a slight change in the dataset. Now, computing the global sensitivity of a function or query is a non-trivial task. Intuitively, we say that a function f is k-sensitive if it amplifies the distance between inputs by at most a factor of k. Formally, it means that for any x and y in the domain of f, if the distance between x and y is less or equal than n, then the distance between the results of f applied over x and y is of at most k times n. Now, how is this incorporated into differentially private systems? Well, there are two options. One is that the framework provides a set of built-in functions whose sensitivity is already known, so the user just selects one of those to compute on the dataset. The clear advantage of this approach is that calibrating the noise is very simple. There is no need to worry about sensitivity computations. But the disadvantage is that we are limited by the set of provided functions. The second option is to have a language that allows user-defined functions and uses advanced PL techniques such as linear and modal types to have a strong type system that keeps track of sensitivity calculation. This approach clearly opens up the possibility for computing more exciting queries, but the biggest drawback is that we will need to implement a new language from scratch. In this work, we explore the possibility of defining a domain-specific language that allows users to define their own functions, and aided by the host language type system, we provide a proof of their sensitivity. With this in mind, we created a Haskell library with two data types. Data type rel NA represents a collection of values whose distance is at most n. This data type is an abstraction of the expression any x and y at maximum distance n that we mentioned when defining the sensitivity of a function. Data type rel comes together with a set of combinators and operators. For instance, we can create relational pairs or vectors and perform binary operations like addition over relational values. The second data type is sen k a arrow b, representing functions from a to b with proven sensitivity k. To create terms of this type, we need to use operator bank, whose type can be interpreted as: if you give me a function that takes any collection of type A with distance n and returns a collection of type B with distance k times n, then I can produce a function from A to B with proven sensitivity k. If we pay close attention, the type of bank matches the definition of a k-sensitive function. This means that having a proof of sensitivity consists on convincing the type checker. Finally, the operator add is used to apply functions with proven sensitivity to relational values. Okay, so how do we use them? The idea is that the user writes their functions using rel operators, meaning that they should be dealing with relational values, and when a sensitivity proof is required, the user can just pass the function as an argument to bank and see if it type checks. If so, we have our proof. Let's check a concrete example. Say we define a simple map that takes as input a function f and a vector. If the vector is empty, it returns empty. If not, it applies f recursively to each element in the vector. Notice that nil and cons are marked in red, meaning that they are relational vectors. We can confirm this by checking the type of map. We can see that it takes a function with proven sensitivity k and a value from a collection of vectors at distance n. And then it returns a value from a set of vectors at distance k times n. Now we define senMap that takes a function f and calls bank over map of f. What is the sensitivity of senMap? The type checker indicates that senMap takes a function from A to B with sensitivity k and produces a function with the same sensitivity but lifted up to the vectors. With this simple interface, we have managed to implement several canonical functions such as fold-L, sum, insert, and sort, and provide a sensitivity proof for all of them. So to sum up, in this work, we have learned that in a strongly enough type language, it is possible to create a library that allows users to define their own functions and prove their sensitivity. We believe these results can later be plugged into a framework for differentially private queries so that the systems do not get too complicated. Thanks for your attention.